All right, so our video for today is going to be all about midsegments and angle bisectors. Our central question here is going to be, what are the properties of midsegments and angle bisectors? Now, when we last left off in the last video, Euclid had moved on to polygons, right? He had started to investigate actual shapes, and he was starting with triangles, and he learned a lot about the different properties of triangles. Then what this says is that Euclid began to explore different types of segments that could be drawn inside of triangles, one of which was the angle bisector. Now, angle bisector, that's a thing that we looked at in a previous video, so this should be nothing special. It's just that it's going to be inside a triangle now. So here's what it says. An angle bisector is a segment through a vertex of a triangle that splits the angle into two congruent angles. Now, triangles have three different vertices. That's the plural of vertex. And so if we draw a segment going through any of those vertices such that it splits that angle into two congruent angles, so we put the little arcs on them because it's congruent, that's an angle bisector. Now I'm going to name those two angles angle 1 and angle 2. And that would mean that the measure of angle 1 is equal to the measure of angle 2, or that angle 1 is congruent to angle 2. Now, since there's three different vertices on a triangle, there's really three different angle bisectors that we could draw. And strangely enough, all three angle bisectors intersect at one point. And that point is called the incenter. This says the incenter is the point where all three angle bisectors of a triangle are concurrent. Concurrent is a fancy word that means that they all intersect at one point. So what we're going to try to do over here is to draw all three angle bisectors. So do your best to draw a segment such that it splits that angle in half. Mark all those angles as being congruent. And if you do it well, all three of those should intersect at one point. And like we mentioned, oops, I meant to highlight that. Like we just said, that point is called the incenter. So that point right there, that is the incenter. Okay, so let's solve some problems with this now. Example 1 says DC is an angle bisector. Solve for x and the measure of angle ACB. Well, if this is an angle bisector, those two angles have to be congruent. And if they're congruent, that means their measures are equal. So I'm going to set them equal to each other. If I subtract the 2x, I get 3x minus 30 is equal to 6. If I add the 30 over, I get 3x is equal to 36. Which means that x must be 12 when I divide. Now, it also wanted the measure of angle ACB, so let's plug that 12 back in and see what happens. If I plug it into 5x minus 30, 5 times 12 is 60, minus 30 is 30. If I plug it into the other side, 2 times 12 is 24, plus 6 is 30. So the two measures are equal, so that's good. And that means that if I add them together for angle ACB, I get 60. So the measure of angle ACB is 60. All right, let's check out example 2. Example 2 says AD is an angle bisector and CAB is 4x plus 10. Solve for x and the measure of angle CAB. Okay, this is a little bit interesting because CAB is this angle, right? That's that whole angle. Now, if AD is an angle bisector, that means that both of these little angles have to be the same. So we can think about this two different ways. I'm going to pose the question to you of how many green angles does it take to make a yellow angle? And the answer is 2, right? Because it got split in half. It's going to take 2 of those to equal the whole thing. So I'm going to do 2 times 3x minus 5 is equal to 4x plus 10. I'm saying it takes two yellow angles, oops, sorry. It takes two green angles to equal a yellow angle. If I distribute, I get 6x minus 10 is equal to 4x plus 10. Subtract the 4x, I get 2x minus 10 is equal to 10. Add the 10, I get 2x is equal to 20, which means that x is 10. Now we always want to check our work, so let's plug that back in. 3 times 10 is 30, minus 5 is 25, which should mean that this side's also 25. And then if I plug it back into CAB, 4 times 10 is 40, plus 10 is 50. So I'm going to give myself a check because I checked my work. And the measure of angle CAB is 50. Oh, I also checked my work on the last one, but I didn't give myself a check mark. Got to give myself a check mark. All right, example 3 says G is the incenter of triangle ABC. Find the measure of angle ABC. Let me write all these things down that I got to find. I got to find ABC. I got to find ACD. And I got to find BAC. Okay, so before I even look at what those angles are, if this thing is the incenter, that means that these two angles are the same, these two angles are the same, and these two angles are the same. Right? That's what an incenter does, because the incenter is where all the angle bisectors meet. Okay, so just off that alone, I know that this has to be 15. I know that this has to be 35. Now let's see if that helps us at all. Angle ABC. That's ABC. That's this angle over here. And that's a 35 and a 35, which should be a 70. ACD. That's this one over here. That's a 15 and a 15. That's a 30. Okay. And then we want BAC. Now, BAC is this big angle over here. Okay. So to do this, we're going to kind of ignore all the lines on the inside. We know what angle B is. It's 70. We know what angle C is. That's 30. Or the big angle B, right? ABC and BCA are 70 and 30. And all three angles, all three big angles, the ones that I've highlighted, that's the triangle sum theorem, right? All three of those have to add up to be 180. So if I do 70 plus 30, I get 100. And then 180 minus 100 gives me 80. So BAC's got to be 80. And then, just in case they wanted us to find, the little ones have to be 40, right? Because 80 divided by 2 is 40. Okay, and that all works, right? That all those add up to be 180. So I'm going to give myself a check mark because I checked it. All right, so angle bisectors. That's a wrap. Let's go to the inside here where it says next Euclid moved on to midsegments of triangles. Now a midsegment is a segment connecting the midpoints of two sides of a triangle. So if I got my triangle here and I find the midpoint over here, find the midpoint of that side, so it splits it into two equal parts. And I find the midpoint over here so that it splits that into two equal parts. Then this segment right there, that is the midsegment. So a midsegment connects the midpoints of two sides of a triangle. And Euclid also proved this other fact, and we might come back later on once we have some more skills. to actually prove why this works. But for right now, we're just going to trust it. And it's the midsegment theorem. And it says that the midsegment of a triangle is half as long and parallel to the third side. So what that means is that if we've got a midsegment here, that means that it's like if the midsegment is 5, the third side's going to be 10 because the midsegment is half as long and it's going to be parallel. So we're going to put those little arrows on there. Let me draw those a little bit better. Let me do them in red actually. So they're parallel and it's half as long. Okay, now both of those are going to come in handy big time. So let's see what example 4 says here. Example 4 has actually drawn in all 3 midsegments. It says DF, FE, and ED are all midsegments. Okay, so before I go anywhere, that means that D is a midpoint, F is a midpoint, and E is a midpoint. Okay, so all 3 of those points are splitting those into 2 equal parts. And they want us to fill in the blanks here and find out what's going on here. Now, something I like to do if I've got all 3 midsegments drawn in is I like to do this coloring pattern. So I know that DF goes with CB, FE goes with AC, and DE goes with AB. So if you've got some highlighters, I would recommend you do that. It's going to really help us associate the sides that go together. So the first part says AC is parallel to which side? Well, AC has got to be parallel to FE. Those are the sides that are going to be parallel there. DF would be parallel to CB. And then BA would be parallel to ED. Once again, because those are the midsegments that go with those third sides. And then they're throwing on some numbers here. They say if BC is 6, so if this whole thing here is 6, then DF would need to be 3, because the midsegment is half of the third side. If DE is 5, and these numbers don't really make sense in scale, but we're just going to roll with it. If DE is 5, then AB would need to be 10. And if AD is 3, then FE, well, if AD is 3, then DC is 3, and this whole thing is 6. So this would need to be 3. Hopefully that coloring pattern kind of helped you make sense of that. Okay, this one, we got some more mid-segments here. DF, FE, and ED are mid-segments, so let me mark some stuff here. And then let me do my coloring pattern. Gonna help me make sense of what's going on. Okay, so the first thing they want us to find is the measure of angle AFD. Now AFD is this angle right here. And if you remember that those yellow lines are parallel, right? Then if you recognize that, then maybe you can see that AFD is a corresponding angle with FBE. And corresponding angles are congruent, meaning that that too has to be 35 degrees. Likewise, ADF, this angle over here, is going to be corresponding with the 75 down there. All right, now where's DEC? DEC is right here. And using those blue lines, that angle's also corresponding with the 35. FEB, this angle right here, using the green lines is corresponding with the 75. Then we've got BAC. Now this one's a tricky one. BAC is, let me see if I got a different color I can use. BAC is this angle up here. Now, if we zoom out and we just focus on big triangle ABC, we've got a 35-degree angle in the bottom left. We've got a 75-degree angle in the bottom right. Adding those together gives me 110. And subtracting that from 180 using the triangle sum theorem, I get 70. So that top angle, BAC, has to be 70 up there. And then, using that, we can do a little bit more corresponding angle stuff and see that BFE, this angle right there, that's corresponding with the 70 up there, using the green lines. So that's got to be 70. And then EDF, where's EDF? EDF is right here. Now that one, that's kind of tricky as well. EDF, that is actually an alternate interior angle with the 35 right on the other side there, using those blue lines. So that's got to be 35. It's a little tricky one to throw in there at the end. Have to do some alternate interior angles as well. Yeah, but so those parallel lines, really powerful stuff there with those mid-segments. Really lets us find some different angles in there. Okay, let's go to the top here, and let's do some solving. All right, so this says DF's a mid-segment, solve for X, DF, and CB. Okay, so if this is a mid-segment, then one of the things we said is that the mid-segment is half of the third side. So if we ask ourselves, how many yellows does it take to make a, how many yellows does it take to make a green? It takes 2, right? It takes 2 of those because it's half as long. So it's going to take 2x minus 2's to equal a 3x minus 16. So that's my equation. Now I can solve. Let me distribute. I get 2x minus 4 is equal to 3x minus 16. If I subtract the 2x, I just have 1x left over there. Adding the 16 over, negative 4 plus 16 is 12. So x is 12. Now plugging that back in, let's see what happens. If I plug it back in, 12 minus 2 is 10. And then 3 times 12 is 36. 36 minus 16 is 20. So that looks good. 10's half of 20. I'm going to give myself a check. And then let me jot down my other answers. DF was 10. CB was 20. Same deal here. FE is a mid-segment. And they want us to solve for X, FE, and AC. All right, so similar process here. Let's double the mid-segment, set it equal to the base. So 2 times 3x plus 3 is equal to 7x plus 2. Once again, the rationale here is that it's going to take 2 yellows to make a green because the yellow is half of the green. So we distribute, we get 6x plus 6 is equal to 7x plus 2. If I subtract the 6x, just get 1x plus 2 is equal to 6. Subtracting the 2 gives me 4 for x. Let's plug it in and make sure that it works. 3 times 4 is 12, plus 3 is 15. 7 times 4 is 28, plus 2 is 30. 15 is half of 30. Check myself, give myself a check because I checked my work. And let me jot down my final answers here that FE was 15 and AC was 30. All right, and the last one says FD's a mid-segment. Okay, divides those in half like that because those are midpoints. And solve for x, y, bf, and bc. Okay, so we got an x and a y floating around here. Now I'm going to focus on the mid-segment first because we're in the groove there. Should take 2 of those yellows to equal to green. Right, 2 times x minus 1 is equal to x plus 7. 2 yellows equals green. We distribute, we get 2x minus 2 is equal to x plus 7. Subtract the x, I get 1x minus 2 is equal to 7. Add the 2, I get x is equal to 9. Let's plug that back in, make sure that works. 9 minus 1 is 8. And 9 plus 7 is 16. Okay, 8 is half of 16, so we're good there. Now, were either of those something we wanted to find? We did want to find BC. So BC is 16. But now we got to find Y. So what's going on with Y? Well, Y is on the 2 sides over there that have been split in half, right? BF and FA. And don't get too carried away with this times 2 business because if F's a midpoint, then BF must be congruent to FA. So for that, I'm just going to do 2y plus 1 is equal to 4y minus 7. No times 2 here because those parts are equal. So subtract the 2y. 4y minus 2y is just 2y. Add the 7. 1 plus 7 is 8 is equal to 2y. Divide by 2, and we get y is equal to 4. And then let's plug it back in, and that should wrap this thing up. 2 times 4 is 8, plus 1 is 9. 4 times 4 is 16, minus 7 is 9. All right, everything worked out. Gonna give myself a check. And what's the last thing I gotta find? BF. And we found that. That was 9. There we go. Okay, so time for you guys to shine here. You got 6 problems over here to try out. 3 mid-segment things, 3 angle bisector things. Give them a shot. Come back when you're ready to see how you did. All right, so first one, angle bisector wants us to solve for x. 7x minus 5 is equal to 4x plus 10. Subtract the 4x, we get 3x minus 5 is equal to 10. Add the 5, we get 3x is equal to 15. So x should have been 5 for that one. For an angle bisector over here, same deal. Let's do 2x minus 5 is equal to x plus 20. Subtract the x, we get 1x minus 5 is equal to 20. Add the 5, and we get x is equal to 25. This one gives us the big angle and the small one. So this should have been a 2 times x plus 20 is equal to 9x plus 5. That's 2x plus 40 is equal to 9x plus 5. Subtract the 2x, we get 7x. Subtract the 5, we get 35 is equal to 7x. So x should be 5. All right, now some mid-segment stuff. Find the perimeter of DEF if those are all mid-segments. Okay, well, if that thing's 12, then ED should be 6. And if this is 8, then FE should be 4. And if that little piece is 5, this piece is 5. Oops. This piece is 5, this whole thing is 10, then this should be 5. So 5 plus 4 plus 6 is 15. Then we got to do a little times 2 business here. Should take 3x's to equal 7x minus 5. That's 6x is equal to 7x minus 5. If I subtract the 7x, I get negative x is equal to negative 5, which means that x is positive 5 if you divide by negative 1. Then the last one, let's do 2 times 5x plus 4 is equal to 6x plus 8. That's 10x plus 8 is equal to 6x plus 8. If I subtract the 6x, I get 4x plus 8 is equal to 8. Subtract the 8, I get 4x is equal to 0, which means that x is 0, weirdly enough. But if that weirded you out, plugging 0 back in should confirm it. 5 times 0 is 0, plus 4 is 4. 6 times 0 is 0, plus 8 is 8. And 4 is half of 8, so it worked. Just weird that x is 0. But that's it for this one. Hopefully you guys are feeling good about it.